Is anybody ready with their whiteboard? Does anybody have something they can present? Somebody's watching television or has some profanity in the background. Can you get rid of that, please? Anybody have number 2 ready to present? No, Madeline, I went ahead and turned the sound on, so you should be able to talk if you want to. Madeline, if you want to talk, you got to hit the phone symbol up in the Join Me, and then underneath the something should pop up, and you hit the little gear icon, and you turn on your microphone. It should work. Hello? Does anybody have number 2 that they're willing to present?
I can present.
Who's this?
Josh.
Oh, Josh. Okay, let me see if I can pass it to you. All right. Okay, so can you take us through this? Can you talk, Josh?
Oh, there we go. I couldn't hear anything for a while.
Okay.
Right.
Can you tell us? Yeah.
So I started off, I put the pivot point at the ball of the foot, and then I found the torque for the force which was given, which was 720 newtons downward, so that would make a counterclockwise torque. So I just did force times lever arm here, which is 720 times 2D, and then that would be 1440 newtons. And then I knew that that torque would be equal to the torque from the Achilles tendon, so I wrote an equation for that torque, and then solved for that and got 480 newtons.
What do you guys think? Well, I don't know if anybody else can talk or not. Well, let me ask Josh in his group, because I'm not sure if anybody else can talk. It does tell you there's a force of 720 newtons, right? Or, excuse me, that tells you the mass is 72 kilograms, which would be 720 newtons, right? So, is that the FB, though?
I guess not necessarily.
Yeah, it would really be the weight, right? Which would be the same as the normal force. So the normal force is... So by you putting the pivot point at the normal force, which is the only one you know, it's kind of like you have 2 unknowns. You're not going to be able to solve it. Where would be a good place to put a pivot point at, Josh, if the 2 unknowns are FT and FB?
Well, if you're looking for FT, then put it at FB.
Right, yeah. So that's where we don't want to put the pivot at the ball of the foot. We want to put it either at the tendon or we want to put it where FB is. So let me go ahead and take the control back from you, and then we'll have maybe somebody else will volunteer. Thanks, I appreciate it.
Sure.
Hey, did anybody happen to put the pivot point at either FB or FT? Anybody be able to present? Okay, one last call. Is anybody able to present? Okay, well, I guess I'm going to go ahead and present then for you guys, which is a little bit disconcerting since we were planning on doing the test tomorrow. If the Twidla site is giving you a hard time because you're putting this web page in, that might be it because we didn't have problems before. Maybe you should just open up a Twidla site and not load this page in. Just do a regular old whiteboard. So in other words, I'm saying perhaps maybe it would be better if it's not loading for you, it's causing problems. Maybe just simply go to the whiteboard and then, you know, draw in, here's the foot, there's a normal force here, and there is the bone force, FB, here, and there's a tension force here, and then solve it that way maybe. I did see somebody had a question of, you know, where's this worksheet at, because I understand you weren't planning on doing this. If you're on the My Big Campus page, if you go to current agenda assignments, you can get the page here, and it'll load up, and it's worksheet 5 we're doing, so you just kind of have to scroll down here. And you can get it that way. That would work. You could do that. Or if you would rather, I made this site here, but evidently some people are having a hard time with the Twidla. Keep in mind that we've already got the Join Me program going, and also we've got the Twidla thing going. So the more things you have going in the background, playing music or anything else, if you have too many tabs going, it's really going to be slowing down your computer quite a bit. So, you know, kind of keep that in mind, so you don't want a whole lot going on. I think I saw Luke said that he could present. So let me see if I can hand it over. Actually, before I do that, Luke, let me copy this. And let me try that Twidla again. I'm going to go back to a web page, type that in. And it pops up here. And then Luke, I think you said that that you could present. So I'm going to see if I can pass it to you. Oops. Try to anyway. There you are. Okay. So Luke, can you talk? No, he's not able to talk, but we problem, I think.
Okay.
Oh, Harry's talking. Okay.
So what I did was, since we knew that we did not know FB or FT, I put the pivot point at FB and then solved for FT, which would be 720 newtons times 2, which is the distance, equals the force, because D is 1/2 of the big D. So that gave me 1440, and then I knew, since we know that all the forces have to balance out for equilibrium, then I could use, since FB was the only force downward, then I could use the 2 forces that I knew to figure out which FB was.
Sounds good. So you use the torque equation. Torque of FB equals torque of FT. Solved it, and you got 1440 for the force of, let's see, that was the FT, and then you were able to find the FB after that. Any questions from anybody? Okay, thank you very much, Luke. I'm going to take it back.
I've got a question.
Oh, question. Yes.
Do you have to factor in, like, your weight force, or is FB included in your weight force? So
okay.
Have the weight force?
Let's go back to the very first equation, the torque FB equals torque FT. For that one, keep in mind that the weight force, if you're only looking at the lever, which is the foot, the weight force is not acting on it. Remember, the weight force is between the mass, which is way up there near their belly button. That's where the center is, and the center of the Earth. that's where the forces are acting. So the only thing acting on this lever, the foot, is FT, FB, and the normal force, which is right there at the ball of the foot. Now, that normal is the same magnitude as the weight, but no, the weight doesn't affect it. Any other questions? Okay, thank you very much, Luke. I'm going to take the controls back. So now we just finished number 2 here. By the way, period 2, you should be able to do number 1. I'm not going to make period 1 do it again. They've done it, but you should be able to do that one. Number 3 here, this is one we're getting ready to whiteboard. Before I set you loose in your whiteboards, because that took a long time, it could be the Twidless side, I'm not sure. But let's talk about where all the forces are. Can somebody tell me where the forces are, or type them in or something? Tell me one of the forces. The person. Okay, so there would be a force downward right where the person is. That would be the normal force on the board from the person, which happens to be the same as her weight. Okay. There any other forces?
Force upward from A and B.
Force at A, maybe. Okay.
Yeah.
Or maybe it's downward. Is it upward or downward?
Up.
Okay. I'm not really sure. For some reason I'm thinking it's downward, but okay, I'll leave it upward. What about B? It's also up. Okay. Okay. Now keep in mind, it's okay if I draw it in the wrong direction. Remember how I'm thinking that it's down, you're thinking it's up. It doesn't really matter. What will happen in the equation, it'll be negative. And any other forces, this is why I'm doing it, because I was worried that you guys wouldn't be able to see this other force. There's one more force. Notice it says the board has mass. Yeah, right, Luke. There's a weight force right in the center of this board from the weight of the thing. So the weight of the board. Right? Okay. So we know the mass of the board. So we know this weight. We know the mass of the girl. So therefore we know the normal force on the board. So we know this one as well. The two unknowns are A and B. So where would be a good place to put a pivot point then?
A.
A. Okay, so let's put a pivot point here. And so then we could say the torque of B must be equal to the torque of those two combined, right? Okay, so why don't you go ahead and get in your whiteboarding groups and solve this problem. Sarah, so can you guys present then, Sarah? Oh. Does that mean you don't have a Sarah? Okay. So can anybody present this problem? Do you want to join? Okay, so I think Ethan, are you saying you're, no, I have it, but I can't. Okay. Ethan, are you able to present? I'm not sure if you're saying you can present or not. Okay, all right. And I think Sarah has it, but she says she can't talk, so we need somebody who can talk. Anybody have this problem worked out that can present it? Do you guys also see there on the Twidla site? I understand that it takes a while to draw, and especially if you're trying to write, there's a text tool where you can just type stuff too. That might help. Thanks, Luke. You already presented, so I'm going to see if I can have somebody else present. Thanks, though, for offering. So we might have to come to you, but I'm hoping somebody else can take it. Kendall has it. So is Kendall volunteering? Can Kendall talk? Or Annie? Who should I give it to? Kendall or Annie? Or Annie? Yeah, who is that? Is that Kendall?
Yeah.
Okay, I will pass it to you then. Here you are. Okay, go ahead and take it.
Torque B.
Okay.
And so you know that B is 1 meter away from the pivot, so you have whatever the force of B is times 1. And then for the torque of the weight of the board, it's 2 meters because it's halfway through the board, and the board is 4 meters long, times the weight of the board, which is 280 newtons, and then plus 520 newtons from the woman times the 4 meters away she is from the pivot point. And then when you multiply those together and add them up, you get that F of B equals 2,640.
Okay, so that makes sense. So again, you just use torque, and you said the torque of B must be equal to the torque of N plus the torque of P. Okay, and so you get 2640. And then what about for FA? How did you find that one then? Or are you still working on that?
I didn't get to that yet.
Okay, all right, okay. So thank you very much. We still need to find the force of A then. I'm going to go and then Gavin, so I'm going to go ahead and pass it to Gavin. Okay. So did you also get 26?
So to find force A, we used the sum of the torque of A. We put the pivot point at B. But
Okay.
the torque of A has to equal the torque of the force from the board and the torque from the person. So I solved for the torque of the person right here and got 1,560 Newton meters. And then the torque of the board, I solved for it. It was 280 Newton meters clockwise. And you use that equation to get torque of A is 1840, and that's 1 meter away from the pivot point. So we got the force of A is 1,840 meters.
Okay, I do have a question, Gavin, though, because look at your picture there, and you put the pivot point nicely at B. Which way would A cause it to rotate, clockwise or counterclockwise? Looking at the picture.
Oh, clockwise. I mixed up the directions.
No, that's all right.
No, they were the same direction.
Yeah, that's what we chose. Remember when we were drawing the free body? We all just kind of. So you found clockwise there, and yeah, you said they're all going in the same direction, right?
Yeah.
But since you said torque of A equals torque of B D plus torque of person, and we all agree with that, can A really be pointing upward?
No.
No, it's really downward. So that 1840 newtons is actually downward.
Yeah.
Okay. Any questions from anybody? Why is it downward? Okay, so I'm going to take the controls back from you, Gavin. Thank you very much,
right.
and I'm going to try to explain a little bit better why it's downward. Okay, so let me try to reload this screen here, see if I can explain a little bit better why that force has to be downward. So give me a second here. Okay, so we definitely know there's a force downward here, a weight. And there's a weight of the board also downward here, okay? We just found the force of B, and we definitely know that that one's upward, so there's no confusion about that one. Okay, the question is, which direction is the force of A? Well, let's put the pivot point here at B. Can you see that this force here, I'm going to call it P. Can you see this force of P will tend to make this board rotate clockwise? Can everybody, or downward, yes, clockwise, right? Can everybody see that? Say yes if you agree with that.
Yes.
Downward clock. Okay, good.
Yes.
Yeah. And can you see that the force from the board itself, the weight of the board, also causes it to rotate clockwise?
Yes.
Yes. Yes. Okay, good. So we've got two torques that cause it to rotate clockwise. Now the board clearly is not rotating, right? So the torque over here at A, which direction must it be to make it balance out? Will it be clockwise as well, or is it going to be counterclockwise?
Counterclockwise.
It has to be counterclockwise, right? Well, if I make my force upward, that's going to cause the board to rotate still clockwise. So the force has to be downward. And right here's the pivot at B. That will cause it to rotate counterclockwise. So Ethan asked me that question. I think Ethan Yeedy asked me that. Does that make sense, Ethan? Or it was Pappas, sorry. I can't remember who it was. Anybody? Okay, Ethan, sorry, I didn't know. All right. Any other questions? Okay, so we started at noon. I still got another 10 minutes. Number 4 here. This is a good one that you need to know as well. So for number 4, we've got this sign that's hanging out at the end of this boom here, this beam. And we're trying to figure out the tension of the wire, and we're trying to find the forces here at the hinge. And before I let you start going on the whiteboard to do this one, I think we need to talk about where all the forces are. acting on the beam. So somebody shout out one of the forces or type it in or something. There's a there's a weight of the sign, there's a tension force. Okay, so there's a weight of the sign. I'll go ahead and put that in. Now, really, that's a tension force, right? But it's the same as the weight of the sign. And Drew, you said a tension. I'm assuming you mean this tension in the guide wire thing. So I'll call that T. Okay. Friction. Maybe a little bit if there's some motion here, but this hinge is going to keep it. So we're going to kind of ignore friction, but in real life there probably would be. Any other forces? Oh, let's see. Yeah, there's a support force at the hinge. Actually, there's two support forces here. There's going to be a vertical and there's going to be a horizontal. So the horizontal is this way. I'm going to label this F in the X direction, I guess. And there's going to be a vertical force. And I don't, which way do you want me to draw this vertical force? Do you want to draw upward? Do you think it's upward? Or do you think it's downward? Annie says up, so I'm going to go ahead and, oh, somebody said down. I'm going to go ahead and draw it up. Annie was the first one. Now, the truth is, if it's down, I will just get a negative sign in my equation. If it's, if somebody else wanted to draw it downward and they were wrong, it would just simply say a negative. So it's not a big deal. So I'll call this Fy. Now, the reason I'm doing this with you guys is because I was a little bit afraid. It looks to me like you guys are missing a force. There's one more force. Yes, the weight of the beam. And where does the weight of that beam act?
The center.
Right in the middle, yeah. So there's a weight of the beam here. Okay, so we know this weight of the beam. It's given. We know the weight of the sign. It's given. So how many unknowns do we have? 3. So where would be a good place to put a pivot point? Yeah, at the hinge. If you put the pivot point here at the hinge, which force will you be able to calculate?
Tension.
The tension, yes. And then once you get the tension, then you should be able to, by doing sine and cosines, you should be able to figure out the Fx and Fy. Okay, so why don't you go ahead and get in your whiteboarding groups and start working on this problem.
Can you first explain why
Yes.
there's also a vertical force?
There might not be. That's a good question. For instance, let's say we find, I'm just making this up, please don't think this is right, but let's say we find the tension force here is 100. Well, then at that point, I know that Fy plus Ty is equal to those two weights combined. So 215 plus 155, so 370, I think. I think I did that right. 370. So then I would be able to find Ty. It might turn out that Ty is 0. It might turn out that way. Or, excuse me, not Ty. Maybe Fy is 0. That's what I meant to say. It might turn out Fy 0. Can you see that there has to be an Fx, though? Because there's going to be a Tx?
Yeah.
Yeah. Yeah. The person asked me about why there's a Fy. Did I answer your question that it might be 0? I don't really know.
Yeah, you did.
Okay. Okay. Go ahead and get in your whiteboarding groups and see if you can solve this one. And again, if somebody gets it and they're able to present, you know, text me or something or say something. I think this is going to be the last problem we do. So the quicker we can get it, you know, presented correctly, quicker we'll be done. Ethan, Papa says that he can, okay. Ethan, oh wait, I think I'm done. Okay, let me go to Ethan's group. He's going to show the tension to us, and then I think we might go to somebody else here. Let's see, there he is. Okay, Ethan. Okay, can you talk at all, Ethan?
Can you hear me?
Yep, we can hear you.
Okay.
So yeah, go ahead and tell us how you got this.
Okay. So you have the weight of the sign and the weight of the beam acting in a clockwise direction, while the weight of the tension, or the sign, or I'm sorry, the tension force is acting in a counterclockwise direction, so they're going to be on opposite sides of the equation. So I said 155, which is the weight of the beam, times 0.85, which is the distance from the pivot point. I said 1.7 meters divided by 2, plus 1.7 meters, which is the distance from the pivot point to the sign, times 215 newtons, is equal to, this is the torque equation for the tension. 1.35 is the distance away times sine of 35, which is the angle. And then I simplified to find that the force was 646 newtons.
Okay. When I did it, I think maybe I might have rounded, but I got 642. It's pretty close. I think it's just rounding. So
Okay.
very well. Any questions from anybody? Okay, I'm going to go ahead and take controls. Thank you very much, Ethan. Let's see. Oops. Okay. Can anybody then present the forces at the hinge, the vertical and the horizontal? Okay, so Sarah says she can. Okay, so I'm going to see if I can go ahead and see if I can find Sarah who can talk now. Okay. Okay. All right. So yeah, Sarah, go ahead and tell us how you.
Can you hear me?
Yep, we can hear you.
Yay! Okay. So basically, you can make a triangle out of the tension force with the vertical force, and then the vertical component of the force and the horizontal component of the force. Of course, the 642 that we found was the tension force is the hypotenuse. So using SOHCAHTOA, you can figure out the FX force, the horizontal component of the force, which is going to have to be, in order to create equilibrium, is going to have to be equal to the horizontal force at the hinge.
Okay.
So that comes out to 526.03. And then if you do the upward force, if you have the vertical force at the hinge pointing up, that plus the vertical component of the tension force along the wire is going to have to be equal to the two downward forces, which are the weight of the beam and the weight of the sign. So the vertical component of the tension force by SOHCAHTOA again, and then 68.33. So 368.33 plus the force at the hinge, the vertical force of the hinge equals the weight force plus the weight force of the beam, which is 155, plus the weight force of the sign, 215. So the vertical component at the hinge is 1.67 newtons.
So it's not very much.
No. I don't know if that's right. I think that's right. I don't know.
Yeah, I got something that's probably rounding. I got 1.76, and again I got up. So, but it's not very much. So I can't remember who asked me that, but you could see that it was almost zero, but it's not quite. So thank you very much, Sarah. Very nice presentation. So I'm going to go ahead and take the controls back. Okay, so I think you guys can all hear me now. Our test is not tomorrow. What we're going to do tomorrow is we'll finish up talking about the center mass stuff that we're doing. We might have another buddy quiz or something, but our test is not tomorrow. I'm not even sure if it'll be Monday, but if it's not Monday, then it'll be Tuesday. What you should be working on is worksheets, the rest of the worksheets in this packet, which is just this worksheet 5 here. You should be able to do number 1, period 2 people. Everybody should be able to do number 5. Now that one's kind of a tough one, but you should be able to figure that one out. Number 6 shouldn't be any problem whatsoever. Number 7 is a doozy. For those people who have been doing this stuff and think this is like no problem, this is cake, not even challenge, number 7 is really hard. And if you think it's easy, you probably did something wrong. Number 8 you should be able to do, no problem. That should be easy for everybody. And number 9, no problem. Okay. So I'm not sure if we'll be able to whiteboard the rest of these, but before the test, I will definitely get the answers, even if we're not able to whiteboard them. Also, you should know that I'm probably going to give you tomorrow, I'm going to give you internet homework to do over the weekend, 7 or 8 problems, just to make sure that you really do know how to solve these types of problems. Any questions from anybody?
You said that there's a possible buddy quiz tomorrow, so
Possibly,
should we
yes.
also prepare for like an individual quiz? Or...
No, no individual quizzes in this section. I really like the idea because this is pretty hard stuff. They really struggled last 2 years over this stuff, and I really like all the conversations I'm hearing in the buddy quizzes, and so I think I want to keep doing that. So the test is really where I'm going to see the individual growth.
Okay, thank you.
Yep. Any other questions?
Oh,
yep.
Yeah, I have a question. I know on the last study quiz, it asked you to list from Grace Fleets like the angular acceleration. Is
yep.
Angular acceleration just it's not the same thing as torque, is it related to it or something?
Yeah, well, what I want you to do is I want you to think back to when we were doing the where everybody stood in a circle and we were kicking the hover puck around. Whenever there is a change in motion, there has to be a net force that causes the change in motion. And so whenever there's an acceleration, there has to be a net force. We also saw that sometimes it would be spinning, so there must have been an angular acceleration. So what causes the angular acceleration, Sarah?
The force.
Well, the force what if I applied my force right through the center? What if I applied my force when I kick it?
Well, it's not going to spin, so there'll be no acceleration.
Right. So how do you have to apply the force?
At an angle.
Yeah, and so what do you call that when a force is applied at an angle off center?
Oh, an angular acceleration. Well,
that's true, but what do we call that force? It starts with a T.
Torque.
Oh, torque.
Torque. There you right. So just like net forces cause accelerations, net torques cause angular accelerations. So therefore, when you're ranking angular accelerations, really what you're ranking is
net torque.
Net torques. Yeah, exactly.
Okay.
So,
thanks.
yeah. Okay. Without me telling you, I wanted you to think it. I mean, I could have just told the answer, but I wanted you to think it and kind of connect it together. I wanted to make more sense. Any other questions from anybody? Okay, so I noticed a lot of people said they had problems with the Twidlet. So I really thought this was a great idea that you could work right on the worksheet, but it sounded to me like it was freezing up. So maybe if you guys can send me some emails and tell me exactly, that might help me figure out what the problem is. Okay, well, thank you for joining this class. Our e-learning day goes well. Thanks. Bye.